What if you fell into a black hole? Time would slow, space would stretch, and nothing would escape, not even light. What if you fell into a black hole? It's a question that's captivated scientists and science fiction writers alike for decades, fueling incredible thought experiments about the very nature of space and time. The idea of plunging into one of these cosmic behemoths, objects with gravitational pulls, so intense that nothing, not even light, can escape, is simultaneously terrifying and profoundly fascinating, prompting us to consider the most extreme consequences of the universe's fundamental law. Let's start by understanding what a black hole actually is, because it's often portrayed in a dramatically simplified way. And that is incredibly misleading when we're trying to understand the potential realities. Essentially, a black hole forms when a massive star collapses at the end of its life, squeezing all of its matter into an incredibly small space, creating a region of space-time where gravity dominates absolutely everything. Think of it like a drain in your bathtub. But instead of water, it is warping the fabric of space and time itself, pulling everything nearby towards a single, infinitely dense point called the singularity. Now, let's imagine you are an intrepid astronaut bravely or perhaps foolishly venturing too close to a black hole, perhaps driven by an overwhelming desire to witness the ultimate cosmic mystery. As you approach, you'd immediately begin to experience something called spaghettification, a term coined by scientists to describe the terrifying process of being stretched vertically and compressed horizontally. This happens because the gravitational force pulling on your feet would be dramatically stronger than the force pulling on your head, causing you to elongate like a strand of pasta, ultimately tearing you apart at the atomic level. But even before that catastrophic event, something far stranger would be happening to your perception of time, a consequence predicted by Einstein's theory of general relativity. According to this theory, gravity isn't just a force, it's a curvature of space-time itself. And the stronger the gravity, the slower time passes relative to someone experiencing weaker gravity. As you get closer to the black hole's event horizon phi, the point of no return where the escape velocity exceeds the speed of light, phi time would begin to slow down for you, dramatically compared to someone observing you from a safe distance. From the perspective of an outside observer, your movements would appear to become increasingly sluggish, your actions taking longer and longer to complete, as if you were moving through molasses. Imagine trying to speak, but every word would stretch out, elongating into an unnervingly slow, drawn-out syllable. A chilling reminder of the distortion of time itself. For you, however, time would continue to flow normally, at least initially, as you're experiencing the relative effects of the immense gravity, a bizarre paradox that highlights the counterintuitive nature of space-time. As you cross the event horizon, the outside universe would essentially cease to exist for you. The light from distant stars would become increasingly redshifted, fading into oblivion as the gravity compressed the wavelengths. The effects of time dilation become truly extreme. Every second you experience could correspond to years, decades, or even millennia passing in the external universe, depending on your proximity to the singularity. Now let's delve a little deeper into the mathematical implications, because the equations describing this scenario are incredibly complex and mind-bending. General relativity predicts that space-time is a four-dimensional continuum of three spatial dimensions, and one of time, soil, and massive objects warp this fabric, creating gravitational wells. The closer you get to a black hole, the more severely space-time is distorted, leading to the dramatic time dilation effects that we've been discussing. Furthermore, the singularity at the heart of the black hole represents a point where the laws of physics as we currently understand them break down, offering a profound challenge to our scientific models. It's important to understand that our current theories simply cannot fully describe what happens at the singularity itself, introducing a significant level of uncertainty into the picture. Think about the concept of infinite density, send the entire mass of the black hole concentrated into a single point fin, and consider the implications for space and time. If space and time are fundamentally linked, as Einstein's theory suggests, then the singularity would represent a place where both concepts are infinitely warped, creating a truly bizarre and potentially unimaginable environment. Scientists are actively exploring these ideas through theoretical physics, attempting to develop a theory of quantum gravity that can reconcile general relativity with quantum mechanics, offering a more complete picture of the universe. The exploration of black holes isn't just about understanding extreme gravity. It's about pushing the boundaries of our knowledge about the fundamental nature of reality itself. While the idea of falling into a black hole might seem like a purely theoretical exercise, it raises profound questions about our place in the cosmos and the limits of human understanding. Ultimately, contemplating this scenario forces us to confront the possibility that our intuitive understanding of space and time might be profoundly incomplete, hinting at a universe far stranger and more complex than we can currently imagine. So, the next time you look up at the night sky, remember those invisible behemoths lurking in the darkness, silently warping space time and reminding us that the universe still holds countless mysteries waiting to be unveiled, perhaps forever beyond our grasp.